Hello everyone, welcome to the new iteration of my Arduino guitar effect. With it you can code up any effect that you can think up that you can code on an Arduino. It's perfect for if you don't like using pre-programmed effects, if you don't know how they work, like I do. This is the full schematic. The effect contains 4 stages. There's a preamplifier, a digital to analog converter, a buffer stage and a filter stage. The preamp is the same as the one that I used in my Distortion 101 video. It is a simple class A amplifier with an AC bypass capacitor on the collector that you can adjust with a potentiometer. The total resistance of the potentiometer also doubles as a collector to ground resistor. It doesn't only function to amplify the signal, but also to change the DC bias of the signal so that the Arduino can always read it, since Arduinos can only read positive voltages. The output of the amplifier gets sent to pin A0. To bias it, I use this little trim pot over here. That's a very nifty way to bias because it works with any transistor as long as you do the pin out correctly. You can check if it is biased correctly by reading the voltage in your Arduino pin, and you'll know that it's biased correctly when it reads 511-ish on the Arduino. I like this design with the AC bypass because it doesn't change the bias when you change the gain. So this first button just changes the gain of the preamplifier. The digital to analog converter. Because Arduinos cannot write analog signals, we need to convert the digital signal to an analog one. To do this, I am using this big resistor setup. Instead of using resistors with half the value, I put 2 resistors in parallel, which does the same thing, since I don't have resistors with exactly half the value of another one. This way you only need 1 resistor type, and as long as you have a lot of the same one, you're good. The input of the digital to audio are pins 4 to 13 on the Arduino, and there's a good reason that I'm using these, which I'll get into during the code section of the video. All these resistors basically just make sure that every bit contributes the appropriate amount of voltage to the total signal. The most significant bit, which is the one over here, needs to contribute the most voltage, so it is closest to the output. And the resistors just form a complicated voltage divider. To troubleshoot the converter, I exported data from my Arduino to Python with the help of this YouTube video. Here you can see a plot of the bits I wrote to the input compared to the voltage that I read from the output of the digital to analog converter. This is also after putting in the buffer stage, which I'll get into later, in case you're confused why it doesn't go from 0 to 1000. Next to it you see how much every individual bit was contributing, but weighted exponentially, so that they should all be on a horizontal line. As you can see, all of them are more or less on a horizontal line, but the least significant bits are a bit less accurate, which makes sense since their small voltage contribution gets more easily drowned by noise. If your setup doesn't have the correct resistor values, you might get a response that looks like this, where the line is a bit wonky, or this, where the line has these gaps in it. I played around with different setups, including putting a variable resistor at every bit so I can individually tune them. In the end, I found this setup worked the best. I just thought it didn't work because I was using pins 0 and 1 together with the USB, which doesn't work apparently. There's also a different setup that uses less resistors, but requires more varied resistor values. You could try going for this if you have exactly doubling resistor values laying around, or if you have the patience to manually tune all of them. I didn't have this, and manually tuning would kind of defeat the advantage of this design, namely that it's easier to put on a PCB, since trim pots are a bit bulky. The buffer stage. During my testing, I found that when I connected my speaker to the output, it would react a bit unstable. So I decided I needed a buffer. A buffer turns a voltage into a same or similar voltage, but with a higher electromotive force. This means that you don't have to draw any current from whatever you're buffering. There are 2 components that are very good at buffering: op-amps and MOSFETs. I actually tried both of these, and here you see the response graphs that I got. As you can see, the op amp struggles a bit at the extremes of the signal because I'm supplying it with the Arduino voltage. If I would give it a larger voltage supply, this wouldn't happen, which I didn't want to have the hassle of setting up. The MOSFET only went into its linear region at around half of the input voltage. This is an easy fix though. All I had to do was add an imaginary 11th bit that is always on. Op amps do have one advantage over MOSFETs in this configuration, namely that they can supply a lot more current, whereas the MOSFET's current is limited by this resistor here. However, this should not be a problem since my audio amplifier doesn't draw a lot of current from the audio input. Filter stage. The filter stage consists of two filters. This button is connected to a low pass filter. Set like this, it doesn't filter anything. Set like this, it only lets low frequencies through. And this is a high pass filter that does the same, but it's in reverse. So this way it doesn't filter anything. This way it only lets high frequencies go through. I hate it when filters steal all of your volume when you're filtering, so I designed this one such that it appropriately boosts the signal when filtering. The reason I hate it when filters steal volume, even though it's easy to reintroduce this volume again with a volume knob, is because you want to search for the right sound when you're changing your filters. But louder sounds always sound better, so you will be biased to whatever sound is loudest. It was a bit of a challenge to both boost volume and remove frequencies with one potentiometer. And it would have been a lot easier if I had one of those fancy stereo potentiometers, but alas, I have to use mathematics to save me. In the end, this is this design that I came up with, and it's quite interesting. They aren't perfect, but as you can hear, they function just fine. I could make an entire video delving into how this filter works. To my surprise, the internet is full of filters that do not have this volume introduction, so it was a bit difficult to figure out how to make this one, and I had to think through it myself. So if anyone wants an explanation of it, please leave it in the comments, and that will motivate me to make that video explaining how this filter works. Arduino controls. Lastly, I have these three Arduino controls. I have two analog potentiometers and one push button, and that's going to allow us to change variables in the code while it's running. Okay, so here we are in the code. Right now I'm only reading the guitar. You can see that in the setup I set pin 4 till 13 to output mode. That's very important. I'm not using the serial, but I have it in here in case I need to bias anything. But it's important that you don't run the serial because that will take the Arduino a lot of time and you will hear that in your sound. I am not using this effect at the moment. Here I read the guitar in the guitar pin, store it on the vel, and then I map this value to a bit. Really, this mapper is just returning the identity, and then I send the bit to the guitar pins. And I do that, this is very important, using this port D is and port B is command. So let me explain this. Port D is pins 0 until 7, and I shift this bit, this value bit up, and then I only change bits 4 to 7. The reason I do it with this port D and not the digital write command is because digital write can only do one pin at a time. And you will hear that in your guitar sound. It will be very staticky and noisy if you do it one bit at a time. But here I first basically write the 4 least significant bits, and then I write the 6 most significant bits. And I do that with 2 commands. Port B is bit 8 till 13. So right now it's just sending it through straight away, so we have kind of a clean tone. Let me show you what that sounds like. And I have some filtering going on, of course, but it's not so important. I can also increase the gain, and then you get distortion. So what is this here? Well, this reads the first control and then it delays our Arduino by a few microseconds based on how large control 1 is set. So that is our first potentiometer that Arduino can read. So if I put this to true and I upload it, now my control is set all the way down, which means it shouldn't delay anything. But you still hear that there is a bit of distortion going on, or delay, or whatever this effect is. And the reason for this is because reading this pin actually takes the Arduino quite some time, which already delays it a bit. So a lot of effects are going to be very difficult to program on an Arduino because it is not meant for this and it's quite slow actually. Now if I intentionally make it even slower by now turning this dial, which makes this X go bigger, then it sounds like this. So that's the effect that I heard earlier in the video. And now you can see that you can change this effect by turning this control pin. Yeah, I'm not using the button and the second control at the moment. One other thing that we can try is, let's say you want to make a bit crusher. What you can do is end your signal with just only having the 4 most significant bits contribute. If we upload that, then it's gonna sound like this. And with some time resolution, filtering, okay. So I'm not going to go into what you can do too much. One thing that you can do is, instead of using this standard mapper, you can use an S-curve, which should introduce some distortion into your sound. And one thing that is probably cool to do, but which I haven't gotten to yet, is letting your button switch between different maps. Well, that was the end of the video. I haven't shown you a lot of coding yet because I haven't really gotten to it. Hope you enjoyed, and I'll see you in the next one. Bye!